Analyzing critical values. Analyzing critical values to determine if they are local extrema. We have a method for finding the absolute maximum and absolute minimum on a closed interval a to b. We substitute critical values and endpoints into f of x to find the biggest and smallest output. But how do we find local maximums and minimums? They can only occur at critical values. At each critical value of f of x, it is possible to have a local minimum, a local maximum, or neither. We have two tests for determining whether a critical value is a local maximum, local minimum, or neither. The first derivative test for critical values and the second derivative test for critical values. The first derivative test for critical values. We assume that f of x is differentiable and we let c be a critical value of f of x. If the first derivative, f prime, changes from positive to negative at c, then f of c is a local maximum. If the first derivative, f prime, changes from negative to positive at c, then f of c is a local minimum. So what's happening here, this translates to, if f changes from increasing to decreasing at c, then f of c is a local maximum. And if f changes from decreasing to increasing at c, then f of c is a local minimum. Let's go ahead and look at the first derivative test visually. We have c as our critical number. Now, if f prime is changing from positive to negative at c, f is changing from increasing to decreasing. So we can see that we would have a local max at c f of c. And if there is a change from negative to positive on the derivative, then f goes from decreasing to increasing. So we can see we would have a local minimum at c f of c. Now, if the first derivative stays positive or stays negative, we do not have a local extremum. So we do not have a local max or local min occurring if there is no sign change. We're going to find the local maximums and minimums of f of x equals this cubic polynomial. So to find local max and mins, we need to find the critical values. So we take the derivative and set it equal to 0. So we get 3x squared minus 27 equal to 0. Add the 27, divide by 3, I get x squared equals 9. So I get plus or minus 3 as the critical values. So now we're going to take the domain of f of x, which is all real numbers, and split it up into intervals at the critical values. So I have negative infinity to positive infinity. I have negative 3 and 3, my critical values. And then we go ahead and pick a test point in each interval. So I'm going to choose negative 4, 0, and 4. And we're interested in the sign of f prime to tell me about f. So I take negative 4 and I think about whether f prime is positive or negative there. So if I substitute in negative 4 here, I get 16 times 3 is 48 minus 27 is positive. So I have positive. If I substitute in 0, I can see that I'll end up with negative 27. So I get a negative value. And if I plug in positive 4, I again get a positive value. So what's happening is that f is going from increasing to decreasing to increasing. So at the critical value negative 3, by the first derivative test, I can see that a change in increasing to decreasing will give me a local maximum. So I have a local max at f of negative 3, which is equal to 34. So we want to include the y value. We would plug negative 3 into the original function f of x. And at positive 3, f is changing from decreasing to increasing. So I have a local min at f of 3 equals negative 74. Here we're going to find the x values of the local extrema given f of x equals x to the 1/3 times the quantity x minus 4. Now we're going to go ahead and ignore the graph here. We need to find the derivative, and to avoid the product rule here, we can go ahead and distribute in the x to the 1/3, which will leave us with x to the 4/3 minus 4x to the 1/3. So that now we can apply the power rule and obtain f prime of x is 4/3 x to the 1/3 minus 4/3 x to the negative 2/3. And to set this equal to 0, we're going to simplify it first. So I'm going to factor out the 4/3 that they have in common, and I'm going to factor out an x to the negative 2/3, that's the smaller of the two exponents, to get 4/3 x to the negative 2/3, and then I'm going to have an x to the first power minus 1. So it's to the first power because when I factor out a negative 2/3 from 1/3, it's going to be minus negative 2/3, which is plus 2/3. So 1/3 plus 2/3 is 3/3, which is 1. So here I'm going to rewrite this because I have x to the negative 2/3, and I'm going to move that to the bottom of the fraction bar to get a simplified derivative of 4 times x minus 1 in the numerator over 3 times x to the positive 2/3 in the denominator. And we're interested in where is this equal to 0 or undefined. So this is equal to 0 where x minus 1 is equal to 0, so at x equals 1, and it's undefined where the denominator equals 0, which is at x equals 0. And both of these numbers are in the domain of the original function. The domain of the original function is all real numbers. I can take x to any x to the power of 1/3, and I can plug any x into x minus 4. So since this is an odd root, I'm fine with negative numbers. So I'm going to create my number line, divided at 0 and 1, the critical values. And I'm going to go ahead and pick test points in each interval. So over here, I'm going to choose -1. Between 0 and 1, I'll choose 1/2, and greater than 1, I'll choose 2. And I'm plugging these test points into f prime, again, to tell me about f. So if I substitute -1 into the simplified derivative, so I'm looking over here at the simplified derivative, the numerator is going to be -1 minus 1, so that's going to give me a negative. And then the denominator, well here, x to the 2/3, since I'm going to square this quantity, the denominator is always positive. So overall, a negative over a positive is a negative, so f is decreasing. When I substitute in 1/2, I get 1/2 minus 1, that's negative, over, again, the denominator is always positive, so it stays negative, I'm still decreasing. And at 2, the numerator is 2 minus 1 on the top, so that leaves me with a positive over a positive, so overall positive, which means f changes to increasing. So at my critical values, at 0 and 1, well, 0, there is no sign change. F prime stays negative, so f stays decreasing. So at 0, there is no local extrema, but at 1, there is a sign change on f prime from negative to positive, so f changes from decreasing to increasing, meaning we have a local min at x equals 1. And we were only asked for the x values of the local extrema, so there's no need to substitute 1 back into f of x. Now let's go ahead and take a look at the graph of f of x. So we can see that at x equals 0, I had a vertical tangent line, which is why the derivative did not exist there. But the function f stayed decreasing, so there was no local extrema. But at 1, we had a change of f prime from negative to positive, so f changed from decreasing to increasing. Here we're asked to analyze the critical values of f of x equals natural log x minus x on the interval from open 0 to infinity. And really we've just been given the domain here because the natural log function can only have positive numbers input into it. So we go ahead and take the derivative of f of x. So we get 1 over x minus 1, which we rewrite as 1 minus x over x. And we want to know, where does this equal 0 and where is it undefined? So this rational function equals 0 when the numerator is 0 at 1 and when the denominator is 0 at 0. But x equals 0 is not part of the domain, so we can go ahead and throw that value out. We're just going to break up our domain 0 to infinity at x equals 1. So let's go ahead and plug in our test points. So we'll plug in positive 1/2 between 0 and 1, and 2 between 1 and infinity, and we'll check f prime's sign to find out about f. So if I substitute 1/2 into f prime, so into my simplified version here, in the numerator 1 minus 1/2 is positive, and the denominator would be 1/2, so positive. So overall I'd have a positive f prime value, meaning f is increasing. And if I substitute in 2, 1 minus 2 is negative 1 over 2. So I have a negative over a positive, overall negative. So I am decreasing on the graph of f when I'm past the x value 1. So I do have a change at my critical value from increasing to decreasing on f. So I have a local max at f of 1 equals negative 1. So I went ahead and found the y value, the actual local max, by substituting 1 into the original function. So it's important we plug it into the original function, not into the derivative, because that will of course give us 0. We know 1 is a critical value. So we're looking for the local max on f. We plug that x value into f. On this example, we're asked at what values of x does f of x equal cosine squared x plus sine x on the interval from 0 to pi have a local maximum or minimum. So we'll go ahead and take the derivative, which gives us f prime of x equals, I need to use the chain rule, so I have 2 cosine x. The derivative of cosine is negative sine x. And then the derivative of sine x is plus cosine x. So now I need to set this equal to 0, so I'll factor out a cosine x. So I have cosine x. On the outside I have negative 2 sine x plus 1 equals 0. And now I'm solving, where does cosine x equal 0? And where does sine x equal 1/2? If I go ahead and subtract the 1 and divide by negative 2. So I want to solve these two trig equations, but specifically on 0 to pi. So cosine x equals 1/2 at the x value, pi over 2, if we're restricted from 0 to pi. And sine x is equal to 1/2. Well, sine is positive in quadrants 1 and 2 with a reference angle of pi over 6. So we have two answers there. We have pi over 6 and 5 pi over 6. So we're going to go ahead and split up our restricted domain from 0 to pi at each of these critical values. So now we'll go ahead and pick our test point values. So here, between 0 and pi over 6, this is 1/6 pi. So what's smaller than 1/6? Well, I'm just going to cut it in half and go ahead and say pi over 12. Between pi over 6 and pi over 2, I'll choose pi over 4. Between pi over 2 and 5 pi over 6, I'll pick 3 pi over 4. And bigger than 5 pi over 6, I'm going to go ahead and choose 11 pi over 12. And we want to know what happens to the sign of f prime to tell us about f. So pi over 12 and 11 pi over 12, we could use some identities and figure this out by hand, but I'm just going to go ahead and tell you when you plug pi over 12 into the derivative function, you end up getting a positive value. When you plug in pi over 4, you get negative, 3 pi over 4 positive, 11 pi over 12 negative. So f is switching from increasing to decreasing to increasing to decreasing. So we're going to have quite a few local maximums and a local minimum. So we have a local maximum here at pi over 6 and one over here at 5 pi over 6. And at pi over 2, I have a local minimum. So we'll go ahead and summarize. So we have local max at x equals pi over 6, local min at x equals pi over 2, and local max at x equals 5 pi over 6. And we were asked at what values of x, so we're not going to substitute these back into the original function. And notice we do have to summarize our work outside of our sign chart because our sign chart is really just scratch work. that's helping us to justify and identify what we're being asked. All right, in this example, we're told that we're given the graph of f prime of x. Find the critical values of f and determine if each is a local min, local maximum, or neither. We'll start by labeling this graph. So this is the graph of f prime of x. This is a derivative graph. So if I want to find the critical values occur where the derivative is equal to 0 or undefined. So this graph that I'm looking at, the derivative graph, I want to know where does this equal 0. That's asking us to identify the x-intercepts. So I can see -2, +1, and +3 are all my x-intercepts, all the places where the derivative is equal to 0. So those are my critical values. So now at each critical value I could have a local min, local max, or neither. So we'll start at -2. So f prime on the left side of -2 is positive, and on the right side of -2 is also positive. So there's no sign change on the graph of f prime. So that means that -2 is neither a local min or a local max. At x equals 1, if I look to the left of x equals 1, the graph of f prime is positive, so I'm above the x-axis here. And then just to the right of 1, I'm negative or below the x-axis. So I have a change from positive to negative. So that means that f, the original function, which we can't see, changes from increasing to decreasing. So that means that at 1, I have a local maximum, since f prime is changing from positive to negative. And at x equals 3, if we look just to the left of 3, we can see that I'm below the x-axis, or negative, and as I move to the right side of 3, I'm positive or above the x-axis, so f must be changing from decreasing to increasing as I move from left to right. I always read graphs from left to right. So here I would describe what's happening at 3 as a local min, since f prime changes from negative to positive. So at -2 is the only location where I had neither a local max or a local min, and that's because there again was no sign change. I had positive to positive. So I'll go ahead and write since f prime was positive and stayed positive. So in summary, regarding reading the graph of f prime, first we need to identify all critical values by finding x-intercepts on the graph of f prime, or any non-asymptotic places of discontinuity on f prime of x, like jumps or holes, because that's when the derivative would be undefined. If the graph of f of x changes from positive to negative at x equals c, or above to below the x-axis, then there is a local maximum at f of c. But notice we weren't able to find, and we cannot find f of c because we don't have the graph of f of x or the equation for f of x. And if the graph of f prime of x changes from negative to positive, on the other hand, at x equals c, or below to above the x-axis from left to right, then there is a local minimum at f of c, but again we cannot find f of c. Now let's look at the second derivative test for critical values. So we're going to have c be a critical value, again, of f of x, and suppose the second derivative is continuous near c. If the second derivative at the critical value c is positive, then f of c is a local minimum. If the second derivative at c is negative, then f of c is a local maximum. So let's go ahead and look at the images that are shown here. So let's say we've identified critical values at x equals 1 and x equals 3. If we know that the second derivative at 1 is, let's say, -6, a negative number, then we know that the shape of the graph will be concave down. Well, if I'm concave down, that must mean I have a local maximum. And on the other hand, if at the second derivative at 3 I end up with a positive number, that must mean I'm concave up at the critical value, which means I have a local minimum. Now, if the second derivative at the critical value is 0, then the test doesn't tell us anything, which is inconclusive. So f of c, it might be a local max, a local min, or it might be neither. We have to go back and use the first derivative test. Alright, in this example we're going to determine whether each critical value of this cubic polynomial function f of x is a local minimum or a local maximum using the second derivative test. So we still need critical values. We still need the first derivative to find critical values. So the first derivative can be found using the power rule, and we go ahead and set this equal to 0, so we'll factor out the 6 and factor the quadratic and end up with the two critical values, x equals -2 and x equals +1. So these are critical values, still obtained by setting the first derivative equal to 0. So we don't want to get confused and accidentally set the second derivative equal to 0. Those are possible inflection points, and we're not doing anything at all with those. So now the second derivative, f double prime of x, is 12x plus 6. And we directly substitute the critical values separately into the second derivative. F double prime of -2 is 12 times -2 plus 6, which is -18. And f double prime of 1 is 12 times 1 plus 6, so +18. So what this tells us, since the second derivative at -2 is negative, what we know about the graph is that the graph of f is concave down. So this would be the graph of f is concave down, so we know that that critical value is a local maximum. So I know that I have a local max at f of -2, which is, substituting -2 into f, 21. And the second derivative at 1 is positive, so that means that f is concave up. So if I have concave up, I would have a local minimum at f of 1, which is -6, if I substitute again the x value into the original function. And in this example, we're asked to find the local maximum and minimum values of f of x equals x to the 5th minus 5x to the 4th. So it doesn't specify which test to use, the first or second derivative test, so we can choose, it's up to us. Now I'm going to go ahead and go straight to the second derivative test. So we're going to go ahead and take the first derivative to find those critical values. So f prime of x is 5x to the 4th minus 20x to the 3rd. I'll factor out a 5x to the 3rd to be left with x minus 4 and set that equal to 0. So I get critical values of x equals 0 and x equals 4. Now, the second derivative is 20x cubed minus 60x squared. And I'm actually going to go ahead and plug in my critical values. So if I plug in 0, I end up getting 0 minus 0, which is 0. And that gives me an inconclusive result. So that doesn't mean neither. It means this didn't really help me. So I'm going to have to go back and use the first derivative test. Now, at this point, it's up to us if we just want to scrap the second derivative test altogether, or if we want to continue and try substituting in +4 and seeing what happens to at least tell us what's going on at 4. So if I substitute in 4, I am actually going to get 320, which is positive. So we did get out one piece of information here. Since the second derivative at 4 is positive, right, I have a concave up graph. So that means that f of 4, which is 704, that's going to be a local minimum. So I know that much. But I am going to have to go back and try 0 with the first derivative test. So I'm going to go ahead and create a little number line here that extends from negative infinity, 0, 4, but I'm actually not going to bother over here with infinity or anything over here past 4 because I only care about what's happening near 0. So I'm going to go ahead and pick my test point, negative 1 in the first interval, 1 in the second interval, and if I think about f prime, so here we have to be careful, we're doing the first derivative test. So if I substitute negative 1 over here, so this is my first derivative, I will end up with a negative times a negative. And overall that is a positive. So I'm a positive first derivative on the first interval, and at my test point 1, I'll get a positive times a negative. 1 minus 4 is negative. So that's going to give me negative. So f changes from increasing to decreasing, meaning I have a local maximum at f of 0, and f of 0 is just 0. So if I plug in 0 and 0 into my original function, I get out 0. So the second derivative test can be quick, but it has a downfall. It doesn't always give us a result. If we get out 0, that's inconclusive, and we can't just stop and say that's the answer. We have to go back and go to the first derivative test. It's just that the first derivative test might be a little more work if it requires an extensive sign chart.